Well, good evening. Welcome to Space Oddities. Thank you for joining us on this Monday evening. Hope you're all well. And I must apologize again if my video is not synchronized with my voice. This is due to an ongoing connection problem I have here in Spain, which I'm trying to resolve with my ISP. But so far it hasn't been resolved. I hope to resolve it this week. So anyway, I know I look like an amateur ventriloquist, but there we are. Anyway, welcome to Space Oddities. If it's your first time here, you are more than welcome. And we hope that everybody's had a good week. And joining me on the show tonight, we have Michael and Roger and Lou and Rachel and Kat. How is everybody?
Fine, thank you.
Good, thank you.
And Daz has disappeared again. He was here a minute ago. So we've got Daz coming in and out as normal because he has an even worse internet connection. So he will keep coming and going. He's here now. Let me just let him back in. So we have quite a packed program tonight. But before we get started, thank you to everybody who's been buying us coffees. That is much appreciated, as always. Thank you to our sponsor, Roller Valley Optics, for supporting us in this little venture. And don't forget that the Space Oddities merchandise is now available. And I just put this up here, and we have the most gloriously wonderful T-shirts in the history of T-shirts for you to strut around in and strut your funky stuff in this summer. Michael is actually modelling the Space Oddities T-shirt. Michael hails from Stourport, and he lists his hobbies as what are your hobbies, Michael? Never mind, we'll come back. And we also, if you would like to buy a Space Oddities T-shirt, they're at the extremely reasonable price of £19. That does include postage and packing within the UK. Please add £10 for foreign orders. And we have also, for your delectation and delight, we have Space Oddities hoodies, which are made of really lovely material. They are obviously a little bit more expensive. They're £35, but again, including UK postage and packing. So if you missed this, the full details are in the description of this video and also at the top of our page on Facebook. And if you haven't joined the Facebook group, why not do it? And also, while we're on the subject, please like, subscribe to the video, subscribe to the channel, comment on the video, because liking and subscribing and making a comment in the video after the event is much appreciated, because that really does attract the attention of the YouTube algorithm. So there we are. So there's the merchandise. We will be releasing more merchandise in due course. But there we are. And what else have we got to say? Well, not much. We've got Rachel, who's rejoined us after having little Isaac. So you're welcome back, Rachel.
Thank you.
Looking radiant as always. And we hope that you don't fall asleep in the middle of the show. Let you stick with us.
If I vanish early, then you know where I've gone.
Okay, now we know exactly where you've gone. So how is little Isaac? Is he okay?
Yeah, he's here. Look, here he is. Look, can you see him?
Oh,
so cute.
Oh, it's beautiful.
Don't I'll get broody.
Does he cry all night?
He's good as gold in the day. He does like cuddles at night. He likes to be held forever. But, he won't be that small forever, so I'm making the most of it.
Fantastic. Okay, so what have we got for you tonight? Well, Kat's going to be telling us all about the rather interesting subject of asteroseismology and how the study of earthquakes on the Earth can assist us to understand seismic movements on other worlds. So that's something really interesting to look forward to. Lou's going to be telling us about the new discoveries about water on Mars. I will be reviewing a year of science from the James Webb Space Telescope. Daz will be talking about colour and how we perceive it, and that's it. But as always, to kick off the programme, we go straight over to the man who is more often than not to be seen looking at the moon. And it's a particular bent of his, as it were. and we know that Roger produces some amazing photographs of the moon. So, Roger,
Yes.
how's the week been?
Other objects are available.
Yeah.
Yes, absolutely. Yes, your solar.
That is no moon.
Well, one must mention your solar pictures. Okay, Roger. So, tell us all about it this week, then.
Okay, so we are working our way through the merry month of July, and we're coming up through to the first half already. There we are. What's happening? So this is something that I haven't seen today, the sun. But as you are noticing down in the bottom left there, that is active region 3363. I will just show you a close-up of that. Here's an image of it in hydrogen alpha. And if it's clear enough for the viewers to see, they can obviously see all the magnetic activity around the spots. Not only that one, but on several of the others. But apparently it is now, as it moves towards the center of the disk, that spot is breaking up. Kevin Earp will know because he's managed to see a bit more of it than I have today. For a comparison, there's the size of the Earth compared to that spot. So it is a fairly large one, but not the biggest one that we've seen this year.
Nice.
And while I was out yesterday in the morning, I took this daytime moon, and it's about the clearest picture I've ever had of it during the daytime. We're just coming up to first quarter, which was today.
That's wonderful. Look at that.
It's beautiful.
It was a very still morning. So we're having the third quarter today. And by next Monday, a week's time, we will be having a new moon. So the phases are getting to an end for the moment. And during the week's night sky, I've got this trained at 10:30 at night because we were just seeing the end of Venus and Mars in the sky at the moment.
Yeah, I noticed Venus isn't there anymore.
Yes, it's getting very low now.
Yeah.
Very low, and disappearing almost completely by the end of the week, really, unfortunately. Yeah. Although we do have the summer triangle high up now in the night sky, with Cygnus almost going right overhead almost. So that's something to consider, and be able to do more imaging of the North American Nebula and the Ring Nebula and a few other nebulas and stuff. But during the wee hours of the morning through this week, there's a nice little meetup of Saturn, the Moon, and Jupiter. And,
oh, nice.
So this will be tomorrow morning, Tuesday, and Wednesday you got the thin crescent Moon and Jupiter, so that's quite nice.
And Uranus there as well.
Yes, Uranus and the Pleiades.
Oh no!
The Pleiades. See, on Thursday it'll be near the Pleiades, but I'm guessing at that sort of time it might not be fully visible enough, really. The brightness of the sky might knock the Pleiades out, but there is a possibility.
Not the Pleiades already.
The Pleiades,
oh, yes.
the Hyades, yes.
I've seen them
there. Anyway, we have got some new information from the James Webb, and I have got some information here. So there's a report here of a black hole that existed 570 million years after the Big Bang, allegedly. So
now that this is still not well understood how these supermassive black holes can exist so soon, in inverted commas, 570 million years after the Big Bang. One leading theory is that what you have is a huge cloud of interstellar molecular hydrogen, which basically collapses under its own weight and spontaneously collapses into a supermassive black hole. So this has got nothing to do with stellar mass black holes that form after supernova explosions, but it's still a challenge to work out this mechanism. And astronomers are not exactly sure, but that's what the Webb is for, after all, to find things like this, so we can refine our theories and work out how these supermassive black holes appeared so soon, again in inverted commas, after the Big Bang.
So does that provide some evidence for which came first, the black hole or the galaxy?
Wow.
Well, I think, looking at it, it is very much a chicken and egg question. And what we do know is that there is this intimate relationship between a supermassive black hole and its host galaxy. So they have grown up together, but which actually came first is still very much open to question.
Good to have a mystery or two out there.
Yeah, I think this has been one of the big, really major discoveries about black holes, supermassive ones, over the last few years, that we've realized how much they influence the evolution of a galaxy. And, they are inextricably linked, the galaxy and the black hole. For example, there's a direct, a perfect linear relationship between the mass of the supermassive black hole and the mass of the galactic bulge. It's a linear relationship, and this is not something that is understood at the moment at all, why that should be. So, they are in effect one beast, the galaxy and the black hole. It's not like they're two separate things that don't influence each other. They are inextricably linked. But anyway, this is good news about the early supermassive black hole. So this will help get the theories in line.
So not only have we got that report, we've got another report where we've got a rather large amount of data here, which has been pasted together for working out. Let me try and find the.
I take it those are all galaxies, are they?
Those are all galaxies there, yes. And
yeah, amazing.
it's trying to put things together into data. So we've
got the spectra there.
Yeah.
A lot of hydrogen.
Yeah, so there's between 540 and 660 million years ago, some of these were formed after the Big Bang, according to this report.
Wow.
And Sears 24 and Sears 23, which are the top two of those three, emitted their light 13.3 billion years ago. And Sears 3 was a mere 13.2 billion years ago. So, quite interesting to work out how all this information is all coming to us all in one go, really. And for the next part, we've got some other parts which have got, these are much younger, only 12.8 and 12.7 billion years ago. Old, and it's just phenomenal, all the studying of these images. And then there's this one, which is dust reservoirs in 2 supernova. And
yes, I saw this. Yes,
so
extremely dusty.
That's a good point from Chris.
What?
Perhaps we need Dr. Becky to join us as a guest speaker on black holes.
Oh, yes.
Indeed.
Yeah, that's her specialist subject, isn't it?
Yeah.
Because talking about galaxies, wasn't there also an image where they think they found possibly a strand of galaxies which were basically the first to form part of the cosmic web?
I'll be talking about that very thing later, Daz.
Oh,
okay, then I'll be quiet. Sorry.
Yeah.
So for these distant galaxies,
right?
Okay. I guess you're not viewing standard candles. You have a redshift. So are they just fitting the redshift to the Hubble constant? Is that how they get a distance? I imagine something like that.
They're using the Lyman break, where the shorter wavelengths are completely absorbed by hydrogen in the galaxies, and that's
Ah,
and that's telling them the distance or giving them an indication along with the redshift.
okay. The degree of absorption.
Yeah.
Yep.
Yeah.
Yep.
Okay, that's what I've had from this week. I've just got the gallery to produce on the show here. So when you're ready for that, let me know.
Oh, okay. Do you want to do it now?
I can do it. There's only two images to show this week.
Okay.
We were a bit thin on the ground on images, so but first
Yes,
one.
those of you who have sent your images in, thank you very much. As always, we love seeing them.
Mm.
Okay.
So,
yes, Jerry sent this one in.
yeah.
Tulip.
Oh, Tulip Nebula with his Esprit 100. Information down there, 17 times 5 minutes, and there we go. So here we go. Dun, dun, dun.
Oh, Jerry, another
Wow.
winner.
Tulip Nebula.
Wow. Oh
Oh.
my. That is certainly something. Holy.
Okay.
It's lovely, that is.
Very nice.
So there's a fill in here. Don't know who this interloper is. Just to prove that I do not do just the moon and the sun. This was from a couple of years ago, where we got about 4.5 hours on the Iris Nebula,
Oh, right.
and there it is.
Wow.
Wow.
Oh, that's lovely,
Oh,
Roger.
Yeah.
Lovely colour.
Mm-hmm. And you can see some of the cloud dust there
Yeah.
in front of some of the stars
Yeah.
there. So,
And you
That's
had
incredible.
4.5 hours of clear skies there in England. That's amazing.
well, Sparkford skies.
Yeah. All right, Roger. All right, Roger.
Unprecedented.
Just go out any random night and just do a big session, and you can just do it straight away, like almost.
Yeah.
But not this year.
That's wonderful.
Okay, right. That's just the gallery that we have for this week.
Thank you very much, Roger.
Thank you.
That's quite amazing.
Thank you, Roger.
Yeah, brilliant. Brilliant. I love the moon photo this week, Roger. Really nice. So, as a lunar photographer,
A
is this
loony photographer.
a loony photographer? Yes,
Yeah.
you heard correctly. Is there somebody in the field of lunar photography who you sort of look up to as being sort of the governor in terms of lunar photography, or do you think you're the governor? Which I wouldn't disagree with.
Right. I haven't really sort of no one in particular really.
No, I just wondered. 'Cause
I'm working on it.
you are, and you're making very good progress. Yeah, you should definitely do an exhibition.
Yeah. Well, I'm preparing a photo book at the moment, so
I was going to say when's the book coming out?
I haven't done one for ages, so I need to do an astrophotography book.
Yeah.
Mm.
You could do it.
Yeah, we have a casino in our village. It hasn't been a casino for many decades. It's sort of just like a communal meeting place now, and quite often we have local photographers sort of just exhibiting.
All right. Yeah.
And selling their wares, and you walk through them and you think, God, these are crap, but they seem to sell them, and they charge exorbitant sums for them. So just an idea, make some money.
Okay.
But there we are. Okay, then moving on. Next on the agenda tonight, we've got a fascinating subject that's been brought to our attention courtesy of Kat, and Kat is going to tell us all about the amazing science of asteroseismology, which until she started telling us about it was not something that I knew a lot about. And Kat, how did you get interested in this? What about this took your fancy?
So I had I was very fortunate to go to Turkey last year and look at data and do a lot of analysis and all that stuff on Turkey, because Turkey is quite a fantastic tectonic plate. It sits on the Anatolian plate and is pushed by the Indian plate from underneath. So there's a lot of movement. It's a very active region. And at the time, I had no idea that, the earthquake that would occur in February would actually occur. And nobody really had any foreground on it. There were no readings. And it was intense. It was there were 2 earthquakes, magnitude 7.5 and 7.8, and as all of you know, there was extreme destruction in Turkey, and it was quite awful. So using this study of earthquakes on Earth, we can use that and analyze moonquakes and Marsquakes on other planets and moons, even asteroids, which I will also talk about. And it's quite phenomenal, actually. And I only got into extraterrestrial seismology as an interest recently, but earthquakes is something that I am a longtime fan of, and I'm very privileged to be working with the data that I have.
Sure. Just one thing. When you left the studio, you lost your presentation, so you're going to have to re-upload.
Oh, I did. Oh,
Yeah.
no, that's unfortunate.
Because if you leave, you lose your presentation. So
right.
So don't worry.
Okay.
What we'll do, I think, found something fairly. Daz, would you like to talk about your perception of colour now? Just while Kat's
My perception of colour. Yes, I can do it. It's a very short presentation.
Just while Kat's re-uploading her presentation.
Yeah, no, that's fine. It's just a very short presentation. And it's just that, just to sort of like give people some idea of when we're out and about and we're looking around the world, how we actually see colour. Now, to astrophysicists, they're always thinking about colour because it can tell them so much. And you can basically see, you can get the distance to the object, and other things which I will talk about in a little while. And basically, it's a messenger. It's a way of inside all the light and the color. There is messages, and it can tell us so much. So we can know how bright it is. We can know where it is in the sky. We can detect it if it's moving. But best of all, we can actually, as we all know, light is made up of more than just one color. In fact, it's all the colors of the rainbow intertwined. And what we can actually do is we can actually break this light up into its spectrum, or into its rainbow, if you want to call it that way. And of course, we've got Mr. Isaac Newton to thank for this. And of course, we can see all the different colors that the light is composed of. So if you've got a star and it's showing you a specific light, you can see basically what sort of light it's emitting by the emission of different colors. And as I said, well, it just says it here, just as I'm reading it. Of course, the light is comprised of red, orange, yellow, green, blue, indigo, and violet. Now, our eyes cannot break this spectrum up into its separate colors. Unlike Geordie LaForge's visor on the Next Generation Star Trek, he can see all the entire spectrum, which is far more superior eyesight than we've actually got. But as we know, as I said, we actually see light, but as I said before, it's a blend of all colors in one, and it's creating, quote, a color image. But there are ways we can split all this apart. We do this in case something reveals itself in one place or another in the actual spectrum. We can identify certain chemical features in an object by breaking down the light into its spectrum. And this is a process that we call spectroscopy. And I noticed Jack's been speaking about spectroscopy in the chat. And if you want to know a bit more about it, if you just go to the Space Oddities archive on YouTube, and you'll find that I've actually done a breakdown of spectroscopy there, a beginner's guide sort of thing. And it's quite, well, I hope it's quite,
if you go to our channel, viewers, there's a playlist there called Space Oddities videos, and you'll find it in there.
Yeah. So as I said, as astronomers, we care and we think a lot about the colours of things. And we can also measure the triumphs in science, the big achievements, by how technology effectively has replaced our physiological senses that we've been using before. Since Galileo, the telescope has replaced our eyes to see far away and small, dim objects. So when you improve our senses, you can make more discoveries that we could not make otherwise. What is the true colour of objects? Right. If you take a ripe apple, traditionally, what colour is it? Anyone?
Which variety of apple?
Don't get technical. Well, any apple, to be quite honest, any apple.
Green.
But
A
generally,
nice green
generally
flower.
we'll say it's red. Generally, we'll say it's red. It's not a golden atrocious. But generally we'll say it's a red apple. And when you say that, the very construct of that sentence implies you are describing something intrinsic, an intrinsic property of that apple. What you're saying is the apple is red and also the apple is round. That is properties of that apple. So you're describing them. But here's the problem. The only way you know the apple is red is because any red light that was in the white light, which is the light we get from the sun, that's illuminated, has been rejected by the apple and sent back to our eyes. Now, as I said, we've got all the colours of the rainbow in, but specifically the red apple that you think you're looking at is only red because the red part of that spectrum has been rejected by the apple and sent back to your eyes. So that is why it looks red. This is good because when you illuminate a scene with white light, the red things reflect the red, the blue things reflect the blue light, and the yellow rejects the yellow light. And that's how we see colours. So what white light is doing is using all those colours in the rainbow within that light to reveal the colour of things. So back to the apple. The white light hits the apple. The only reason why the apple is red is because it's rejected the red light that was in the white light and that it was fed, and it's absorbed all the other colours but rejected the red. The rejection of the red we're seeing with our eyes, that's why we call it red. That's why we're calling it red, because the red light is sent back to us and that's what we see. But there is no red in, around, or amongst that end part of that apple, because the apple has sent all the red back to us. The actual true colours, so our very language that says the apple is red is logically flawed, given that what I'm telling you about the light. The colour of the apple is orange, yellow, green, blue, indigo, violet. That's got stuck into the skin of the apple. That's all been absorbed into it. That's what it is. What it is not is red. Now we can just accept this colloquially, that a red object is red, okay? And we can just say that. But if you go to the surface molecules of the red object, there is no red there. It all got sent back to you. Let's take this further. If you have light that contains no red light in it, so an ultraviolet light or a very narrow or a very yellow sodium lamp, what we used to have in the old street lights, and what you do is you take the apple and bring it up to that lamp. You know what color the apple is? The apple will be black.
Oh.
The apple will absorb all the colors it is receiving from the light source, but because that source contains no red, there is nothing for the apple to reject, no red to reflect back to your eyes. My point is, when white light hits the apple looks red because it reflects only red light and has absorbed all the other colors. Now we have a light source containing no red light. It's got to be black. So the apple will actually look to our eyes. It will actually look black because there's no red to be sent back. By the way, under the same lamp, a blue object will still appear to be blue, a yellow object will still appear to be yellow, and a green will still appear to be green because they are rejecting the colors that are still present in that light that it's being bathed in. This is the same for every color we see. Leaves are green because the leaf surface rejects green light out of the white light. A blue car, the paint of the car rejects blue light, so we see a blue car. The point is, whatever color you think an object is, that is the one color that object is not. So how's that to mess with the brain?
Oh, there
So
you
that's
are.
all I wanted to say.
Thanks.
Yeah.
Oh,
That's
wow.
fantastic. I mean, yes, this whole business of color is a bit weird, really. It's just as well that when we say red apple, we know exactly what we mean.
Yeah.
Yeah.
It's just the light that's been rejected by that object, the color in the white light that has been rejected, and that's what we see.
Yeah.
So that's the one color that object is not.
No, exactly.
And next week I'll be talking about the color of the sun.
Fantastic. Because that's a good question. What color is the sun? Dun, dun, dun.
Wait until next week.
Okay. All right.
I'm not giving the punchline away.
Yeah,
Thanks,
Daz,
Daz.
I was
Okay.
going to say, from an early age, I was diagnosed as being technically colourblind. It is between in the red and the red and the green, and things that I can't do. You know, the spot pictures that you get. You're supposed to try and find a pattern in the picture. I can't actually do most of those, and so that's where I fail my sight when I do the tests. So yeah.
Well, I was the same because I remember doing those tests at about the age of 12 or 13 at school. Yeah. And they said...
also, you know these 3D images that you used to get on the printed on a... I can't remember what they were called. The
Magic Eye ones?
Yes, yeah. And,
I never had a problem with those.
Oh, I did. Very rarely I could see what I could do, but
they're quite amazing.
The thing I can do, I can use virtual reality, a virtual reality headset, and see everything that's going on.
Oh right,
that's different. I don't know.
Well, I mean, I had to have a chat with the careers advisor at school because they said you're red green colourblind. So, what do you want to do for a living? And I said I want to build traffic lights.
Yeah.
So they said no, that's out. I'm afraid. They said anything else. I said I wanted to be a pilot because I did at the time, and they said no, you can't do that.
No, they just told me that I couldn't be an electrician.
Oh, well, yeah.
I can understand why.
And
it seems to have started a bit of a conversation in the chat. Steve Warbis says there is one African tribe that has a totally different concept or perception and description of colour to us. So, well, that's interesting.
Yeah.
Jack Martin says pink lady apples have highest concentration of flavonoids. Graham Turvey, so an orange is actually named precisely what it isn't. Yeah, of course it is. Yeah,
absolutely.
It's
absolutely.
It said, what's the colour of the wind? Blue, eh? What's the colour of the wind? Blue. Bernard. Yeah, okay. That.
Even for you, that is
great contribution, Bernard.
I'm so glad you're not in here tonight.
Yeah.
So
incredible.
And Jack's also trying to pry out of me what is the true colour of the sun.
Yeah.
You'll have to wait.
It's green.
And Ian says it's green.
Absolutely.
All right, let's move on. Kat, finally.
Yes.
So, asteroseismology. So, what's this all about then? So,
great.
Here we go.
So, fantastic. So, hello, everyone. I'm going to do a very short about me. So, I'm going into my 4th and final year at the University of Toronto. I'm studying a specialist in planetary science with a major in archaeology, and I'm also minoring in math. So, throughout my academic journey so far, I have been very fortunate to work alongside brilliant mentors and colleagues who have inspired and guided me. And again, thinking retrospectively, the experiences that I have had with data collection and analysis in Turkey would end up significantly humbling me and motivating me to explore the developments and insights and what we gain from studying our own planet and the travesties within and how they can be applied to the study of celestial bodies. So this is something that means quite a lot. I'm very happy to share this with everyone. So I would like to do a very quick land acknowledgement from Toronto, as it is customary to express my gratitude towards working and living on this beautiful earth. So I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and I am grateful to have the opportunity to work on this land. So we do this at the University of Toronto frequently because the Indigenous community at the University of Toronto is very prevalent, and they do a lot of great work for us, and it is very important to acknowledge this in every presentation that we give. So today I will be showcasing the exploration of celestial tremors and their profound implications for our understanding of the universe. So seismology is the study of seismic waves and their sources. It has been traditionally focused on Earth. However, with recent advancements in technology and space exploration, they have provided us with unprecedented opportunities to expand our knowledge beyond our home planet. So by studying seismology in extraterrestrial settings, we can unlock hidden secrets about the geophysical processes and history of celestial bodies. So the significance of understanding celestial tremors cannot be overstated, as it enables us to understand more about the formation, the geological evolution, potential habitability of that planet. So in the past decade, technological breakthroughs in space missions have revolutionized our ability to study seismology beyond Earth. So instruments like the Seismic Experiment for Interior Structure, or SEIS, on NASA's Mars InSight lander, which I will talk further about later on in my presentation, and planned missions such as Artemis for lunar seismology have paved the way for new discoveries and advancements in this field. So seismology is the scientific discipline that focuses on the study of seismic waves. They are vibrations that continuously propagate through the Earth or other celestial bodies in response to an energy release, such as earthquakes. So we use this data to then understand more about the structure, the composition, and dynamics of that particular body. So the identification of seismic events, such as Mars quakes or moon quakes, as we like to call them, allows for the investigation of subsurface processes. So seismic events can occur at different you move into the Earth due to the changing temperature and fluidity of the medium that you are in. So the variety of the materials influences the behavior of the seismic waves, and since they encounter different densities, elastic properties, and chemical compositions, this results in variations in wave velocities and transmission characteristics. So layered structured bodies like the Earth possess almost distinct boundaries and transition between different materials and physical states. So seismic waves can reflect, refract, and attenuate at these interfaces, leading to complex wave interactions altering their propagation paths. So study these reflections and refractions to infer the presence, the thickness, and properties of various. So also an absence of an atmosphere leads to the reduced wave attenuation, resulting in longer travel distances for some seismic waves and potential interference with reflected waves. Next, I will be elaborating a little bit more on plane waves in seismology. So before delving into the extraterrestrial, I will use the Earth to define the basic understanding of seismicity and how waves propagate through different mediums. So pertaining to propagations, a plane wave is a theoretical wavefront that extends infinitely in all directions and travels in a straight line. So this is what seismologists use to have a solid foundation and understanding of wave directions. Plane waves exhibit properties such as wavelength, amplitudes, and directions of propagation. So when they approach the surface of the Earth, it encounters various layers with different properties, including density, elasticity, and composition, as I previously stated. So at the depending on the differences in the properties of the adjacent layers, the plane wave can undergo these processes such as reflection, refraction, and transmission. So specifically, reflection occurs when the wave is bounced back from the interface, while refraction refers to the bending of the wave as it crosses the interface. Transmission, on the other hand, refers to the passage of the wave through the interface into the next layer. So when these plane waves reach the surface of a body, it can generate surface waves, and those travel along the interface between the solid or fluid medium of the body and the surrounding medium, such as the atmosphere or the vacuum of space. So next we have earthquakes. So this is just pertaining to the earthquakes and the waves that are formulated when the earthquake occurs. So these different types of seismic waves are generated, and these are caused by a natural phenomena that occur when there is a sudden release of energy in the Earth's crust. So this is resulting from seismic waves that propagate through the ground. These seismic waves carry valuable information about the earthquake's source and Earth's internal structure. So the first type of seismic wave we encounter during an earthquake is called a P wave, also known as the primary waves or compressional waves. So P waves are the fastest waves and can travel through both solids and fluids. They have several distinct characteristics. So first, they cause particles in the ground to move in the same direction as the wave propagation. This results in a very back and forth motion, which is seen on the graph on the top left of your screen. That is just a visualization of P waves versus the other waves as well. So secondly, P waves, secondly, the P waves, they compress and expand the material as they pass through it. So think about it like a slinky, how it compresses and stretches as it moves through the Earth. So P waves also have the ability to travel through the Earth's layers, including the liquid outer core. So that's very, very cool. The next type of seismic wave is the S waves. So they are known as the secondary or shear waves. And these waves are slower than the P waves and can only travel through solids. They exhibit different characteristics compared to that of P waves. They cause particles in the ground to move perpendicularly to the wave propagation, resulting in a side-to-side or up and down motion. So unlike P waves, S waves cannot travel through fluids or the Earth's outer core. So both P waves and S waves are examples of body waves, which are waves that travel through the Earth's interior. So they interact with the various layers of the Earth and give us valuable information about the body's composition and structure. So next we have seismology beyond the Earth, finally. So challenges and opportunities. So seismology, traditionally focused on studying seismic waves on Earth, is now venturing beyond our home planet. So seismology beyond Earth involves the study of seismic activity and the behavior of seismic waves on celestial bodies such as planets, moons, and even asteroids, which is super exciting, and I will talk all about that very soon. Seismology beyond Earth presents unique challenges that set it apart from studying seismic activity on our planet. So let's explore some of these challenges together. Primarily, we have limited data availability. This is a very important thing that we cannot really grasp just yet, and it's the obtaining the seismic data from extraterrestrial bodies is a very significant challenge due to the limited number of missions equipped with seismometers. So data collection may be limited in terms of duration, spatial coverage, and the number of seismic events that are recorded. There are also issues with different geological compositions. So celestial bodies have diverse geological compositions. They range from rocky planets to icy moons, which can significantly impact the behavior of the seismic waves. So it's not going to be very consistent, especially pertaining to what we have on Earth. And understanding how these seismic waves propagate through these materials requires adaptation of traditional seismological models and analysis techniques. Lastly, we have complex wave interactions. So again, very different from Earth. Seismic waves interact with layers, boundaries, and subsurface structures in very, very complex ways, leading to extremely complex math, which I could talk about, but I really don't want to, for both the sake of time and the sake of your sanity, leading to very profound issues in the reflections, refractions, and scattering of these particles. It's very dense, to put it plainly. These interactions pose challenges in accurately interpreting the seismic data and extract meaningful information about the interior of celestial bodies. So despite these challenges, however, seismology beyond Earth presents remarkable opportunities for expanding our understanding of the universe. So some of these opportunities include studying planetary processes, super duper important. Seismic activity on celestial bodies reveals vital information about the geological processes such as tectonic activity, volcanic eruptions, and impacts. And understanding these processes helps us to comprehend the geological history and dynamics of these environments. As well, we can advance our comparative planetology. So comparing seismic activity and the properties of celestial bodies allows us to draw connections and identify the similarities or differences between them. So this comparative approach contributes to a broader understanding of the formation and evolution of planetary systems. Very cool stuff. Next, I'm going to talk a little bit more about the Mars InSight mission. So, hallelujah. Launched by NASA in 2018, they have provided unprecedented opportunities to study the seismic activity on Mars. So let's go into more of the significance of this. The Mars InSight mission's primary objective is to investigate the deep interior of Mars and shed light on the planet's geologic evolution. So the InSight lander, equipped with advanced instruments, including the Seismic Experiment for Interior Structure, as I previously said, SEIS, has been studying Mars's seismic activity to understand the internal structure of Mars. The Seismic Experiment for Interior Structure is a state-of-the-art seismometer deployed by the Mars InSight mission, playing a pivotal role in studying the seismic waves of Mars. So the seismic data collected by the Mars InSight mission is of immense importance to the field of extraterrestrial seismology. And essentially, this is why, again, the Martian interior is, we don't know a lot about it, so this will obviously help us understand the geological composition. And since we know that it's a very geologically active planet, studying its seismic activity allows us to gain the insights into the composition and the movement of the waves through those mediums, which we do want to know more about. Also, with the comparative planetology is very important. Mars is very close to us, and there's a lot that we can do in terms of comparing these graphs one to the other, and it will help us enhance our understanding of the fundamental principles that govern planetary formation and evolution, especially within our solar system. As well, this gives us insight into planetary habitability. Very cool. Seismic data from Mars provides valuable information about the subsurface conditions and potential habitability of Mars. So understanding the geological environment and identifying the regions with stable subsurface conditions is critical for future exploration and potential colonization efforts, which we will likely do because our Earth is quite hot. And most of you may know this, but it was the hottest day on Earth as of Monday. And the record was broken on Tuesday, which is quite crazy. There were 2 world records broken consecutively 2 days in a row. So that is certainly something to keep in mind when it comes to climate change. Now, very cool stuff. Lunar seismology. Moonquakes, or seismic events on the moon, have provided fascinating insights into the lunar geology and have yielded very intriguing discoveries. So some of the cool facts about the recorded moonquakes are as follows. Moonquakes can be categorized into 4 main types: deep moonquakes, shallow moonquakes, meteorite impact moonquakes, and thermal moonquakes. So the deep moonquakes occur approximately 700 kilometers below the moon's surface and are thought to be triggered by tidal forces exerted by the gravitational interaction between the Earth and the moon. Second, shallow moonquakes have epicenters located closer to the surface and are believed to be caused by tectonic activity or thermal stresses within the moon's crust. Third, meteorite impact moonquakes have been induced by the impact of meteorites colliding with the moon's surface. So they generate powerful seismic waves that provide valuable data about the moon's structure. Lastly, we have thermal moonquakes. So lunar temperature variations, particularly during the lunar day and night cycles, they lead to thermal expansion and contraction of the moon. So this results in smaller scale quakes known as thermal moonquakes. So some surprising discoveries that moonquakes have revealed. Moonquakes can last for an extended period of time, with some seismic activity lasting for days, and some shallow moonquakes have been observed to have repeating patterns, suggesting ongoing geological processes. The analysis of seismic data helped estimate the thickness of the moon's crust, which is believed to vary between, I would say, approximately 30 and 40 kilometers. So that's 18 to 24 or 25 miles in thickness. Some more very interesting topics include seismic network expansion. So the planned Artemis program by NASA aims to return astronauts to the moon and establish a sustainable lunar presence. So as part of this program, new seismometers will be deployed to expand the lunar seismic network. This enables a more comprehensive understanding of moonquakes and provide valuable data for future lunar exploration and potential resource utilization. Next, we have the implications for lunar science. So study is our understanding of the moon's geological evolution and the presence of subsurface structures and the potential for resource extraction. So again, this is very vital for future missions, lunar-based planning, and potential human settlements. Coming up next, it's called Asteroid Seismology. So the first confirmed asteroid seismic event was, I believe, in 2021, and scientists reported the first confirmed detection of a seismic event on an asteroid. So the event was recorded by NASA's InSight lander on Mars, which picked up the seismic waves produced by the impact of the Mars InSight mission's heat probe on the surface of the asteroid known as 16 Psyche. That's Psyche. And this landmark event marked the first direct evidence of seismic activity on an asteroid. Also, we can study these asteroid interiors. So seismic waves generated by impacts, internal fractures, or other geological processes provide information about the internal structure of asteroids. So by analyzing the characteristics of these waves, we can infer details about the size, shape, composition, and even the internal layering of the asteroid. And we can also differentiate between solid and rubble pile asteroids. Asteroids come in various forms, including solid bodies and rubble pile structures held together by gravity, solely gravity. Seismic studies can help differentiate between these types by examining the propagation and attenuation of seismic waves. So this knowledge is crucial for understanding the formation and evolution of asteroids. We can also characterize asteroid impacts. So seismic monitoring of asteroid impacts on celestial bodies such as the moon or Mars can provide insights into the properties of both the impactor and the target body. So by analyzing the seismic waves generated by such impacts, scientists can study the energy released, the depth of the impact, and the resulting structural changes. Also, something really cool that NASA has been working on for quite some time right now, at this time, is planetary defense. And this is something that a lot of people do want to go into because it sounds really cool, and it is as cool as it sounds. So by understanding asteroid seismology, and this has implications for planetary defense efforts. So by characterizing the internal structure and composition of near-Earth asteroids, we can assess their potential threat and develop strategies to mitigate the impact risk. Next, we have Python implications, applications in extraterrestrial seismology. So Python is extensively used by NASA and other space enthusiasts for analyzing extraterrestrial seismology data due to its versatility, ease of use and the availability of specialized scientific libraries. So here are some ways that Python is used. We have data processing and analysis. So Python scientific libraries such as NumPy and Pandas are leveraged to process and analyze these seismic data that are collected from extraterrestrial missions. And these libraries offer efficient data manipulation capabilities, statistical analysis functions, and tools for handling larger data sets, allowing researchers to extract insights and patterns from the data. We can also perform seismic waveform analysis, which is something that I am currently doing as well. Python, along with libraries like OBSPy, enables analysis and visualization of seismic waveforms. So researchers can read, filter, and process waveform data using array manipulation capabilities. And additionally, Python's plotting libraries, such as matplotlib and plotly, aid in visualizing seismic waveforms and extracting meaningful information from the data. We can also perform seismic event localization and characterization, machine learning and pattern recognition, many different types of data visualizations, numerical modeling, and collaborative and open source development, which is very important in geoscience, where Python's collaborative and open source nature promotes knowledge sharing and collaboration among researchers and space enthusiasts. And projects and code libraries are often shared publicly, allowing for community-driven development, code reusability, and continuous improvement in analyzing extraterrestrial seismology data. Next, we have data processing and visualization. So in the data processing section, we have pre-processing, which is the raw seismic data that is collected from the missions, often requires pre-processing to remove noise and correct for instrument responses and align timestamps. So Python offers functionalities to pre-process and clean the data, ensuring its quality and reliability for further analysis. We can also perform signal analysis. So Python also provides tools for signaling processing, allowing for researchers to analyze and extract relevant information from seismic waveforms. And techniques such as filtering, Fourier analysis, and spectral analysis, wavelet transforms, all of these things can be employed to characterize the properties of seismic signals and identify distinct features. In terms of the data visualization, again, we can do waveform plots. So these plots display amplitude and time domain representations of seismic signals, spectrograms. They are also created in libraries such as matplotlib and provide time frequency representations of seismic signals, helping to identify the frequency content and temporal variations in the seismic data. Event location mapping. So this is the magnitude information, the spatial distribution of the seismic events, and the geological features on maps to gain insights into the patterns of seismic activity. And there's a whole ton more that you can do, including animation and time-lapse visualization. It really does not stop there, and there's so much that you can do, which is why when you go into geophysics, you tend to get some training in these seismology, computational seismology interactions, and it's very important, especially when it comes to graduate school, when you need this kind of background information to work with professors on these topics and further your knowledge on data processing and how you can benefit the field of seismology from beyond Earth. Lastly, we have signal processing and filtering. This includes noise removal, Fourier transforms, filtering, time frequency analysis. Again, all of these are very essential techniques in extraterrestrial seismology to extract valuable information from seismic waveforms and remove unwanted noise. And we also have something called waveform envelope extraction. So the envelope of a seismic waveform represents the amplitude variations over time and provides insights into the energy content of seismic signals. So Python's signal processing capabilities, combined with techniques like Hilbert transforms and bandpass filtering, these enable researchers to extract and analyze the waveform envelope, aiding in the detection and characterization of seismic events. We now have computational modeling and inversion. So inversion is a computational technique that aims to extract information about the subsurface properties of a body by comparing observed seismic data with model predictions. I will be talking a little bit more about this when I discuss the research that I do, because I work with moment tensor seismic inversion, which is quite a mouthful, but it essentially is the creation of plots and graphs that are visualizations of the seismic events that occur on Earth into something that most people can understand, and it is very readable. So it's not something that's just numbers. And inversion helps researchers to infer the internal structure, the composition, and properties of these bodies by observed seismic data with model prediction. So it aids in refining and updating numerical models, improving our understanding of the subsurface conditions. Also, we have forward modeling, which refers to the simulation of synthetic seismic data using known equations. So Python allows us to perform forward modeling by numerically solving wave equations, such as the elastic wave equation, through finite difference or finite element methods. Again, this is beyond the scope of what I would like to discuss today, but something that I would briefly like to touch on is the uncertainty quantification, which the computational modeling and inversion also facilitates this method, which involves characterization and quantifying of uncertainties associated with the derived subsurface properties. So Python libraries like PyMC3 offer tools for probabilistic modeling and sampling, enabling researchers to assess uncertainty in the estimated model parameters. So now on to the fun stuff that I have been up to. So the goal of my research is to use code kindly made publicly available to us by the MTUQ team at Princeton, that's MTUQ, to model and analyze the Turkey earthquakes that happened just this past February. So essentially the MTUQ package provides resources for calculations involving moment tensors from seismic data. So MTUQ has a very smart system that allows for taking in data and using that data that pulls from IRIS, which is a network of many stations with publicly available data from around the world. And OBSPy is the package that acquires the waveforms from IRIS, and PySep is the wrapper that sorts it into the right format and does quality control. So to characterize a seismic event, the moment tensor is used. It is a symmetric 3x3 tensor describing the force coupling in each Cartesian direction. And the displacement measured by each station is a combination of Green's functions and that moment tensor. And so the game that is played is to figure out the original moment tensor based on the displacement and what we know about Green's functions. So we have everything laid out for us. It's just the creation of that beach ball kind of thing that you're seeing on the top right corner of your screen. That is a beach ball, or the moment tensor of that specific earthquake. This is from the 7.8 magnitude earthquake that happened in Turkey, as you can see on that map. And if you look at the bottom left, or bottom right of your screen rather, you will see the waveforms that that line up almost perfectly. We're still working on the data and making sure that the waveforms fit, but it's essentially looking at the observed data and the perspective data, and if they align, and we're trying to make that align right now. And this is all really fun stuff. You can check out check out all possible origins and force sources, determine which, in combination with their associated Green's functions, best match the data for the displacement at each station. So this gives us adequate information to deduce the likely origin point and moment tensor of each individual event. So that is it for my presentation. I don't know if I'm allowed to take questions, but if anyone has any questions, please feel free to ask me. I'd be happy to answer them. Thank you for listening to my very long-winded presentation. I didn't believe.
Kat,
there's a lot to digest there. Thank you, Kat.
And you're welcome.
By the way, viewers, this was Kat's first presentation for Space Oddities, the first of many, we obviously hope. So well done, Kat. That was really interesting.
Yeah.
And,
thank you very much.
Oh, by the way, big hello to Kat's mum who's watching. So, and if I was watching, I'd be very proud. So yes, thank you for joining us, Cat's mum. So there we are.
I've just got one point to make. Kat mentioned P and S waves,
Yes.
and she's probably heard of this lady, Inga Lehman.
That does.
She, by using mathematical equations, she used them to analyze the P and S waves passing through Earth during earthquakes. And by doing this, she actually discovered that we actually have a solid core, which is sat in a molten metal sloshing around sort of thing. So she actually discovered that by studying P and S waves and using mathematics, that the Earth has an iron core. And also she was one of the longest lived scientists in history, living to 104 years of age.
Wow.
So yeah.
Wow. By the way, yes, of course you can take questions, Kat. We'd be upset if you didn't. So the first question is from Steve. Would it be worth dropping measurement buoys onto, for example, the Tiger Stripes of Enceladus to measure seismic activity and surface movement?
I would say so.
That's got to be a yes, hasn't it?
I would absolutely say so. I think that I think that you should put any effort into seismic analysis and understanding of seismic events, regardless of the type of celestial body that you are looking at. All of this information is extremely vital to forming a kind of universal map of these different bodies and how their seismic events are related to where they sit on or in the universe. And that's very important for us to understand. So the answer is definitely yes.
Yes, definitely. All sorts of lovely comments coming through, Kat.
Because also, I mean, Graham Turvey was talking about the ASLEP packages that were dropped on the moon by the Apollo chaps. Of course, they were working up until 1977 when they were switched off due to budgetary concerns. But I bet you wish that they were still working now.
Do you know what? I actually remember watching the moonwalk where they were setting the ASLEP up. I remember that very clearly. Because that was quite a big job, because they had all those solar panels to set up and everything else. It was great. Yes,
did a little research with those lunar surface packages. It turns out they have mass spectrometers on them, and every now and then, perhaps from lunar quakes or an asteroid hit or something, a little particle will flip up into the air. Well, no air, and fall down into the mass spectrometer, and we can measure that. So technically, the moon has an atmosphere.
Yes, it does. It does. About the thinnest.
Another question, sorry, was when you were talking about P and S waves, Chris asked, are these waves independent or does one cause the other?
So if you look, that's a very good question, actually. So, sorry, did I miss something?
No, go on.
Okay, fantastic. So essentially, when we talk about the PNS waves and the body waves in general, one essentially follows the other. You must have one following the other. So I'm not too sure about them causing the other. I think Lou would be more fitted to answer that question in particular, but definitely pertaining to the PNS waves, when we graph them, they are all on one graph. So I think there was a part of my presentation where I showed these waves in a graph form and how they relate to one another. I'm not quite sure where they are. Here we go. So yes, so on this section over here, we see the seismogram that recorded this earthquake, and we notice that the P wave is very small but very fast, and then follows through to the S waves and then the surface waves. So this is just in sequence with one another. You cannot have an S wave without a P wave, as the name follows, the primary and the secondary waves, or the shear waves. So yes, they definitely affect one another, I would say. I'd say that the strength of the P wave or the strength of the S wave will be reliant upon the strength of the P wave, but them being directly related, I'm not too sure about.
Okay, thank you. Yep. Right. Okay. Any other questions out there? Okay. Right. Well, thank you very much, Kat, and very interesting.
Absolutely.
Perhaps you can come back and update us regularly on your research.
Absolutely, I will. Thank you.
So that would be lovely. Okay, well, as time's getting on, what we've decided to do, I'm going to tell you all about the first year of James Webb Telescope science next week. And Lou is going to do the same with his presentation about water on Mars. So we're going to defer those to next week. But there we are. So,
Andy,
yeah.
Remember, we have our special guest next week.
I was just about to mention that. So make sure, viewers, that you are here next week, because we have a very special guest joining us next week. You may be familiar with him from YouTube, but he is the Angry Astronaut, who has a widely watched YouTube channel where he got his nickname by railing and ranting against the space industry. And he's a fascinating guy, and he makes fantastic videos. Go check out his channel, The Angry Astronaut. And we're very, very happy and honoured that he's going to come and join us on the show next week for a chat. So that's next Monday, of course, at the usual time, 8 p.m. UK or 3 p.m. EST. So there we are. And on that, just one final thing before we go. Thank you again to all of us, all of you who buy us coffees regularly. If you'd like to buy us a coffee, which all helps us keep the channel going, of course, helps us pay the bills, then you can scan the QR code there and buy us a coffee. Don't forget that we have the T-shirts and hoodies available now. Full details are in the description of the video. And if you have any questions, you can always mail us about anything, really. And our address is spaceodditieslive@gmail.com. That's spaceodditieslive@gmail.com. And, we're always thankful to hear from our viewers. We love hearing from you. So if you've got anything to say about the program, anything you want to see or learn about, or anything you don't like, or, ransom notes, kidnap demands, death threats, anything like that, you can send them all to spaceodditieslive@gmail.com. So next week, as I said, we have the Angry Astronaut as our guest. Lou will be talking about water on Mars. I will be talking about the first year of science from the James Webb Space Telescope. And I've no doubt we'll have some other odds and ends to throw into the program before then. But from now, I'd like to say a good night to you all. Thank you so much for being here. We do appreciate it. Don't forget to subscribe to the channel if you'd be so kind. And like the video and write a comment afterwards in the comment section on YouTube, because all of that really helps us. So thank you. And we will be back, as I said, at the same time next week, 8 p.m. UK, 3 p.m. EST. So until then, say goodbye, guys.
Goodbye, guys.
Bye, all.
And
Bye.
especially thank you to Kat for that wonderful presentation, her first for Space Oddities. So we hope you do another one soon, Kat, because that was great. Goodbye to Kat's mum as well.
Yes.
Say goodbye to Kat's mum, everybody.
Bye, Mom.
Bye.
Okay, thanks, guys. See you next week. So from all of us at Space Oddities, take care, look after each other, have a fantastic week, and we'll see you again next week. Bye-bye.